to be able to tell you about our experiment, which really has raised a question. Do we have an anomaly in an anomaly? And so I'll talk about the first results from our Fermilab Muon g-2 experiment. Let's get a laser pointer. Okay, so April 7th and April 8th, it was absolutely shocking to us that there were all of these newspaper articles about our little experiment. And the question, the New York Times headline was, "A particle's tiny wobble could upend the known laws of physics." Okay, so that's a little bit of hype. And so what I want to tell you about is, well, what was all that fuss about? Can the known laws of physics really be overturned? What is Muon g-2? How does the experiment work? What did we find and what happens next? So first, I want to thank all of my collaborators on the experiment, the Muon g-2 collaboration. It's composed of people from, well, at least institutions from 7 countries, 35 institutions, 203 collaborators. So China, Germany, Italy, Russia, South Korea, UK, and USA. But then even within these institutions, there are people from all over the place. So it's really fun. It's very international, and it's really a great group to work with. So first, I want to talk a little bit about the standard model and particle physics and what the whole goal of some of this stuff is. So we know that our everyday world is actually made up of just a few relatively simple things. It's made up of just these particles I'm showing you here. So there are these up and down quarks, and they're bound together by gluons to make protons and neutrons. And then there's also electrons, which are bound into atoms using photons. Okay. So photons carry this electric force that binds electrons to nuclei. So we sort of have these particles, the electron, up and down quarks, and then we have these force carriers, so the photon and the gluon. And all of our world, everyday world, seems to be made up of these, just these particles. But of course, new particles have been discovered. Okay, so for instance, we found these particles called muons and tauons. And then there came neutrinos. And then there were more quarks, the charm quark, the strange quark, the top quark, and the bottom quark. And then there were even more force carriers. We discovered the weak force, the W bosons with Z bosons, the electromagnetic force and the strong force. And what I've drawn here is just a bunch of pictures here, but together, these particles and the forces are something we call the standard model. So these are the particles and the forces of the standard model. And I've just drawn some pictures, but really this is a fairly sophisticated model, and there's lots of mathematics behind it that tells you how all of these things interact and work together and give us almost all of the phenomena that we see, at least in physics. So it's very, very, it's a comprehensive and very, very successful theory. Okay. How successful? Let me show you. So does the standard model work? So let me tell you about something called the electron magnetic moment anomaly. This is related to what we're going to study or talk about later today. Okay, so there's this famous experiment. It was carried out by Jerry Gabriels at Harvard. And what they did is they got a single electron and they stored it in something called a Penning trap. So what that is you make a vertical magnetic field and you put a charged particle inside it, and the charged particle will go around in a circle. Okay, that will keep it going in a circle, but to stop it from going up and down, you have to use some electrodes. So you put positive and some positive charges on there, and then that confines the electron in the vertical direction too. And so they would have this single electron and they trapped it for months, and they observed its properties. One of the properties they observed is this something called the electron magnetic moment anomaly, and I'll talk about what that is in just a second. But just to give you an idea about the standard model, So the standard model, all of that mathematics I showed you was used to predict this property of the electron called the magnetic moment anomaly. And here's the prediction. I mean, this is crazy, right? Look at the number of digits in that. And that's just not fake numbers coming out of your calculator. Those numbers are meaningful. And when they compare that with the measurement, this is what they found. And it's absolutely amazing, right? The measurement and the prediction agree. Look at all of these digits of agreement. Okay, the results agree to 10 significant figures. This is the most accurately verified prediction in any field of human knowledge. This is the best we've done in science. It's absolutely amazing. So the standard model, it's fantastic. It's so good. On the other hand, there's some real problems with it, some huge problems. So for instance, there are lots and lots of things the standard model does not explain. So for instance, you probably didn't notice, but I didn't, or maybe you did, in that little picture of the standard model stuff, I didn't talk about gravity at all, even though gravity is one of the most obvious forces. The other thing is that the standard model only talks about 5% of the universe. Okay, so the stuff that we're made of, the atoms, the electrons and atoms and molecules and that sort of stuff, that only constitutes about 0.03% of the universe. Most of the rest of the mass of the universe is in neutrinos, it's in stars, and it's in free gases. However, there's this enormous mystery that there's something called dark matter that constitutes 25% of the composition of the universe, and dark energy, which constitutes 70% of the sort of energy density in the universe. And we have no idea what those are. They're huge mysteries. So, if we were to give physics a grade, we only got 5% right, and we're missing 95%. So, we're kind of failing at the moment, and we just can't tell the other scientists that we're so bad. But we have a lot to do. It's like we have a lot of homework left to do. There are other mysteries too. Like I showed you this table of the particles. Some of them are very light, some of them are extraordinarily heavy, and we have no idea why. We also have no idea why there are these three families of particles, right? We have the up quark, down quark, and the electron. And then there was this duplication with the charm quark, the strange quark, and the muon, and then yet another duplication. So there are these three families. We have no idea why. And another outstanding mystery is, why is the universe seemingly made of matter? Like, you would think that in the beginning we would have equal amounts of matter and antimatter, but when we look around, all we see is matter. So we have to, physics has a lot of things it has to try and do. Okay. So how are we going to make progress on this? Well, we're going to use the scientific method. Okay. So what we have to do here is propose improvements to the standard model. Okay. So we have to figure out what dark matter is. We have to figure out what dark energy is. So part of these improvements may involve proposing new particles or new forces. Okay, so not that long ago, a very popular model was called supersymmetry, and it proposed a whole new set of particles, basically a partner for every standard model particle. And whenever theorists make these suggestions, they're encouraged to make a testable prediction. So something we can go out and see, okay, is this really the way nature works or not? So some of the ways we can test these predictions is we could look for these new particles in high energy collisions. So you can go to the Large Hadron Collider, collide some protons together and see if you find any of these new particles which were predicted. You can also look for new phenomena, like just something new that you just didn't expect before. The other way, which is mostly what I'm going to talk about today, is you could look very, very carefully at the behavior of the standard model particles. So we could take the particles we know, and we could just probe their interactions very, very carefully and see, if they're affected by the interactions with these other new particles. So that's going to be our plan. Now, the thing is, this standard model is incredibly successful. It's been around since the 1970s, and no new particles have been parts of the standard model, like the top quark and the Higgs boson, and so those were predicted in the standard model, and those have been found. But beyond that, no new particles have been discovered, no new forces have been discovered. There's no differences in behavior compared to the standard model predictions. It's absolutely amazing how successful the standard model is. And this is an article a couple of years ago. Supersymmetry, which was something that was a great hope for physics. Here in this article, they say supersymmetry may be the greatest failed prediction in particle physics history. I mean, so we know there's new physics. There's dark matter, there's dark energy. We know there's something new out there. The standard model is incomplete, and we're just struggling really hard to find out what's going on. Okay, so there was a clue, like, so the question is, where do we look for this new physics? How are we going to find these answers? Well, there was a hint of where to look, and that's from the Brookhaven Muon magnetic moment anomaly. So we talked a little bit about the electron. Now we're talking about a different particle called the muon, which comes from the second generation. And we're going to use that approach I mentioned earlier. What we do is you make a very careful prediction, you make a very careful measurement, and then you see if they agree. Okay. So here's the way things stood about 3 or 4 years ago. This is a measurement of the muon magnetic moment anomaly, and I'll talk about what that means in just a second. Okay, so here's the experimental result. This was the value we got, and this was the uncertainty. So these bars over here tell us how uncertain we were about the final answer. This is the prediction of the theorists. So the theorists are extremely smart, and they can figure out what this muon magnetic moment anomaly should be, and this is what they came up with. And you can see that these guys differ, right? The experimental result is different than the theoretical prediction. Okay, and it's significantly different, 3.5 standard deviations. Okay. So this is a hint, but in physics we like to have 5 standard deviations different. So we want to see a really big spread between what we measure and what you predict. And when that's really large, then you can say, okay, now there's something serious going on that we just cannot ignore. For the moment, this is not serious enough to say that, okay, that we have to throw out the standard model. It's not a discovery yet. It's just very intriguing. So let's talk about what is a muon and what is a muon magnetic moment anomaly. Okay. So muons are particles that are just very similar to electrons, right? You remember them from this table. Here they are over here. They're in the second family. So they have the same charges as an electron. They have the same interactions, but in some ways they're quite different. Muons are different from electrons because they're much, much heavier, about 207 times heavier, and they're also unstable. So if you could hold a muon in your hand, it would only last about 2.2 millionths of a second before it would decay. That's the same with all of these other particles in the second and third families. They all decay basically instantaneously, except for the neutrinos. So the other thing is, muons are not found in ordinary matter, of course, because they decay, right? However, they're produced all the time, and they're produced in cosmic rays. So up in the atmosphere, we're continuously bombarded from particles from, other galaxies or even our own galaxy. And these particles interact with material in our atmosphere. So one thing in particular, so these very, very high energy particles come down, they collide with nuclei and electrons in the upper atmosphere, and they produce new particles. So one thing I want to draw your attention to is one of these interactions is, one of these cosmic rays come in, it produces something called a pion. That's this guy right here. This pion will go and then it will decay. One of the things it decays into is a positive muon and a neutrino. If you look at another one of these interactions, you can follow this chain over here. It's another pion. It also decays into a muon and a neutrino. And this one over here, here's another pion. It also decays into a muon and a neutrino. And if you look down at ground level, actually most of what we see are these muons. These are the ones that survive all the way down to Earth. Okay, so muons are there, they're around us all the time, mostly from cosmic ray interactions. And they give us a hint about, if someone told you, okay, please make a muon, well, nature is telling us how you make a muon. It says, make a high energy particle, collide with something, you'll probably get some pions, and try to capture the decay products of the pions. It's a kind of recipe for how to make muons. Okay, so we talked about what a muon is. Let's talk about a magnetic moment. Okay, and here we're going to have to do some work. If you're not a physics major or a science major, you can tune out for a couple minutes and then join us back. But let's talk about a magnetic moment. Okay, So first, let's talk about how you can make a magnetic field. So there are only two slides, I believe, that has some equations on it. This is one of them. So here's how you can make a magnetic field. Okay, you can take a charge and have it run around in a circle. Okay, and you will make a magnetic field with that. And in particular, you can make something called the magnetic moment. And the magnetic moment, which I indicate here with this M, its magnitude is given by the current times the area of the loop divided by the speed of light. So I'm using these special units called CGS units. Okay, let's figure out what the current is. Well, the current is the charge divided by the time it goes around the loop. So there's the charge, and there's the time it takes to go around the loop. And then I just carry over these factors of A over C. Okay. Let's figure out the time it takes to go around the loop. Well, that's going to be the circumference of the loop divided by the velocity. So there's the circumference of the loop divided by the velocity. The area of the loop is pi r squared, and I'm going to multiply on top and bottom by m. So you can see there are going to be some cancellations, right? Like this r is going to cancel one of these r's. This pi is going to cancel this pi. So I can write this magnetic moment as E, so the charge divided by the mass of the particle, times mvr. mvr, some of you may recognize as the orbital angular momentum. So this magnetic moment is equal to the charge divided by the mass times the orbital angular momentum. Now, one of the discoveries early on in the 20th century was that you don't just need an electron going around in a big loop to make a magnetic moment. Fundamental particles by themselves will have a magnetic moment. And instead of using this orbital angular momentum, the particles have an intrinsic angular momentum. Okay. So it's like they're spinning themselves. And the magnetic moment is proportional to the charge to the mass, the spin angular momentum, and then this little factor out in front, which is dimensionless, called the g factor. So here L is the angular momentum. S, which is this new thing for fundamental particles, is the spin angular momentum. And particles have an intrinsic spin and intrinsic magnetic moments, M. Okay. And the great thing, back in the 1920s, Paul Dirac, one of the, great physicists, predicted that G is equal to 2. So he predicted the value of this thing. Okay, so what we're going to want to do is measure a magnetic moment. Okay, so how do we measure a magnetic moment? Okay. Oh, I'm missing a slide. Okay. So this is the other slide with equations. After that, we're done. So you can go to sleep if you want and come back in a minute. Okay, so how do you measure a magnetic moment? Okay, so we're going to talk about torques. Torques are things that make things rotate. Okay, and you exert a torque by applying a force at a distance r from some pivot. And if you do that, you will change the angular momentum of a system. Okay, so here's the case of a bicycle wheel. We'll talk about that in a second. But I want to take the example of what happens with a magnetic moment. If you have a magnetic moment and you put it in a magnetic field, you will also get a torque that will change its angular momentum. Okay. So in the case of the spin of a particle, the spin of a particle will change if it has a magnetic moment and you put it in a magnetic field. And so, so what you'll observe is that the spin will precess. Okay, maybe some of you have seen this demonstration where if you get a bicycle wheel spinning and you suspend it, this bicycle wheel will be seen to be rotating around. We call that precession. Okay, and the rate of that precession would depend on the axis, the length of this vector r, and the force of gravity on it. Okay. For the spin precession of a magnetic moment, it depends on the size of the magnetic moment and the magnitude of the magnetic field. Okay. So this is a key relationship. We'll go back to that in a second. Okay. So again, if you apply a force at a distance r, you will cause something to precess. And in the case of a magnetic moment, if you have a magnetic moment and a magnetic field, that will also cause a particle to precess. Okay. So I'm going to pause here and try and show this video. Sorry for the delay. I wasn't able to embed this, so I do want to show you this because it's kind of neat. So this is a bicycle wheel processing. You know, it's pretty amazing. I just love that. Okay. Okay, so just going back there. So the same thing that caused that bicycle wheel to precess, in our case, that's caused by a magnetic moment in a magnetic field. And what we want to measure is how fast it goes around. Okay, this is the thing we're going to be very interested in. And you'll see that how fast it turns around depends on the size of the magnetic moment. And this is really the thing we really want to measure. Okay, so you may remember when I wrote out the expression for this magnetic moment, it had a little g factor out in front. This is just a number that Dirac predicted, and he said it was 2 for a point-like particle. Now, back in 1933, Otto Stern measured the g factor for a proton, and he found that it was 5.6, like it was completely different than what was expected. And people didn't know what that meant at the time, but now we know that this was an indication that protons have internal structure, that in fact protons are made up of up quarks and down quarks that we talked about earlier, and gluons as well. Okay, so this was a big clue, but we just didn't know what to do with it at the time. However, people looked at electrons, okay, and they measured the g factor of the electron, or indirectly. And so back in 1947, Cushing Foley, they measured the g factor of the electron. That's why I have the little e here for electron. And you can see it's slightly different than 2. This number in brackets is this sort of uncertainty. It means that this 38 here could be 38 plus 10 or 38 minus 10. There's a little bit of uncertainty in the measurement. But the thing that was clear was that the g factor of the electron was greater than 2. Okay, so it's not, it differed from what Dirac predicted. So a natural question would be, does the electron have some sort of internal structure? The same way the proton did. The deviation is much smaller. It's not, nearly as dramatic as that was for the proton. But it's telling us something, right? The fact that it's greater than 2 means something. So what could it mean? Well, at the same time, 1947, Julian Schwinger calculated that the g factor of the electron should be 2 times 1 plus a little bit. Okay, this little bit is called the magnetic moment anomaly. And so he predicted that this should be the g factor of the electron. And if you compare it with the measurement, you see that they agree. It was amazing. Okay, so this little bit extra here is the magnetic moment anomaly. And so you can see if you want to solve for this anomaly, it's equal to g minus 2 divided by 2. So that's why I talked about this experiment as the g minus 2 experiment, because we're interested in this anomaly. Okay, and it's tiny, right? It's 0.001162 or so. The other interesting thing about this was what's the cause of this anomaly? Well, it comes from quantum corrections. The idea that particles are never alone. Okay. So here's a kind of fanciful way of imagining what's going on. If you could have an electron, it would interact with a magnetic field by exchanging a photon. So we talked about that earlier. These were the particles of the standard model. And so this would be how a sort of magnetic moment, a magnetic interaction would work. So electron scatters off of a photon from a magnetic field. Okay. What Schwinger showed is that something else that goes on here is you can get this additional exchange of, we call it a virtual photon. Okay. you have an extra particle in here. And its contribution, it makes a contribution to what happens to an electron in a magnetic field. And this is the so-called Schwinger term. And it was verified by experiment. So this absolutely happens. Okay. Now, interestingly, or one of the amazing things is that it's not just limited to the exchange of one virtual photon. Like, why not? Maybe there could be 2 virtual photons exchanged, or 3. What stops that? And in fact, if you want to figure out really what goes on with the magnetic moment, you have to figure out all of these possible contributions. So you put all the particles you know about into these virtual loops. Okay, so you can have a virtual photon. It makes an electron-positron pair that gets reabsorbed as a virtual photon and reabsorbed by the muon. You could have these other particles I talked about, these other force carriers, the Z bosons, the W bosons, even the Higgs boson appears in these loops. And all of these things change the magnetic moment of the particle. So the interesting thing is that these magnetic moments get contributions from all physics. So all of the standard model particles will appear in these loops, and they will change the value of the magnetic moment anomaly. Okay. So remember, the anomaly is the part by which it's different from 2. And the crazy idea is that if there are particles in nature that we don't yet know about, they will still appear in these loops. Whether or not we know about them doesn't matter, right? If the particle is there, it's going to perturb the properties of the muon. And that's what makes this kind of experiment interesting. So here's the game plan. Maybe the anomaly, the magnetic moment anomaly of the muon, could be affected by new particles not included in the standard model. And maybe that's why it didn't agree, the experiment and the prediction didn't quite agree. So here's the plan. Theorists will predict a mu, I'll call it, based on the particles in the standard model. And us experimentalists, we're going to measure a mu with very high accuracy. And then we're going to compare the prediction and the measurement. If they disagree, it's interesting, right? It could be new physics because there's something new in one of these virtual interactions here. But agreement is interesting too, or helpful, because if you make a new theory of nature, you would be asked to please predict the magnetic moment anomaly of the muon, and your answer better be consistent with the measurement. So as we shrink our error bars, it gets harder and harder for you to make a theory that works. Okay. So doing a better measurement helps us. We can either find new physics, or we can make it, we can squeeze what models are allowed to be very, very few, and we sort of hone in on those that are possible. So one thing, just to correct sort of what you see in the newspapers, let's suppose we find a discrepancy. Well, it doesn't mean that the standard model is wrong. It just means that it's incomplete. Like there's things in there that are not included yet, like the dark energy particles or dark matter particles. It's the same way that Newton's laws are not wrong. It's just that they break down at particle speeds near the speed of light. Okay, and so that we would need a better theory, which is Einstein's theory of special relativity. So, no matter what we found, it's not that the standard model is wrong. It's just that we have to add things to the standard model. Okay, so let's talk about the first part of the game plan here, theorists predicting a mu. So there's a group of theorists who, for 4 years now, it's actually a group of more than 100 theorists, they've all worked together to make a prediction for the standard model value for a mu, okay? And so they came out with a paper not long ago. It's 166 pages. It's really a very comprehensive look. It's tons of calculations. It was an incredible amount of work. And they made a prediction for a mu using the physics we know about. And one thing, it's very, very impressive, right? Look at all of these digits, and they're all meaningful. Like this is a real number. There's nothing, they believe that this number is accurate up to 43 in those last 2 digits here. And it's accurate to 370 parts per billion. This is better than you can predict the properties of the hydrogen atom, which is an interesting idea. Okay, so that's what the theorists did. Okay, how do we do the experiment? Okay, so we're going to need muons, obviously. We're going to make a magnetic field, or we need a magnetic field to make the muon spin precess, the same way with the bicycle wheel would precess in gravity. We're going to measure that precession frequency, omega, the same speed that the bicycle wheel was going around. And then to know to extract the magnetic moment, we have to know the magnetic field. And so we'll measure that by putting protons in the magnetic field and measuring how fast they go. So this is the whole heart of the experiment. A mu, the thing we want, is the precession frequency of the muons in a magnetic field divided by the precession frequencies of protons in the same magnetic field times some constants. Okay. So the last experiment to look at this, I already showed you the answer, is was done at Brookhaven National Lab, so out on Long Island. It's called E821. And the idea was muons were trapped in this storage ring. So there's a big magnetic field and the muons were trapped in it. They'd go around in circles. And as they go around, this muon spin would precess. And what we wanted to do was, okay, if we want to do a better experiment, we're going to use basically the same approach. But rather than make a new ring, which would cost $30 million, we decided to move this ring here from Brookhaven to Fermilab, okay, which is just outside Chicago. Okay. Now, if you look at this and someone tells you, okay, please move this to Fermilab, if you're like me, you would say, that's impossible. And so I'm so glad that there are people who can dream big, okay, who can look at a seemingly impossible job and say, okay, we're going to do it. Because if you look at all of these wires and cables and conduits and cryogenics, it really looks like something impossible to do. But if you break it down and you say, okay, we'll do it in these little bits, it finally becomes something that can be accomplished. But in the beginning, it looked absolutely impossible. So, it's just an amazing, the Brookhaven experiment was amazingly complex. I mean, just look at all of these wires had some purpose. Here was this old, you have to look at this stuff and say, oh, okay, what am I going to do with this? Do I want to keep this? Do I want to remake it? It's really, it was really, I really applaud the people who decided, okay, let's do this. Let's go for it. Okay. So we decided to do it. And actually some of these pictures are when I went out there to start to take the thing apart. I helped with that. And it really seemed like a monumental task. Let me show you something called the big move here.
How would you move a 15-ton, 50-foot wide magnetic ring in one piece without twisting more than 3 millimeters? Slowly and carefully. Sailing down the East Coast, around the tip of Florida, through the Gulf of Mexico and up the Mississippi to Illinois, the world's largest electromagnetic ring, Muon g-2, is moving from Brookhaven National Laboratory on New York's Long Island to its new home at Fermilab in Illinois. Scheduled arrival, July 26th. By land, Muon g-2 creeps along on a specially designed 64-wheel trailer. By sea, it moves by barge. The entire 3,200-mile trip cost about $3 million, roughly 10 times less than building a new ring. What's the purpose of the big move? Well, the ring creates a powerful magnetic field, allowing scientists to store a special subatomic particle called a muon, similar to an electron, but 207 times heavier. Forming only in extremely high-energy situations like nuclear bombs, they decay in just 2.2 millionths of a second, that is, without the electromagnetic ring. Fermilab has the ability to generate more muons than any other accelerator in the United States, but they have no ring. Hence the move. The ring is the mechanical backbone of the experiment. After arrival at Fermilab, it will be fully equipped with instrumentation and upgraded from its Brookhaven days. NSF has provided ongoing support for certain instrumentation and some university-based members of the G-2 team, beginning prior to the Brookhaven experiment and now looking forward to a new era of measurement at Fermilab, an era that could lead to exciting new discoveries in particle physics.
Okay, good. It started to show the next video. Sorry about that. Okay, so one of the crazy things, in addition just to getting this thing on this barge, once we got it in Chicago, they had to shut down 2 interstates. Like you could imagine, saying I have to shut down the Long Island Expressway. Like, it's just a huge undertaking. One of the other crazy things was that this ring, it had to pass through these tollway arches, and there was only 6-inch clearance on each side. And this special rig they had, it could move the ring over sideways, so that the driver would try to go through the center, and then they would wiggle the ring sideways so it would just fit. It just barely made it. We were so lucky. Okay, so we made this special building just for this ring, and it had to be very, very stable. It has this huge, thick concrete floor because we had to have this magnet be very, very stable. And this is what the reassembly looked like. Let's see if that's going to run. Right. So we had to put the whole thing back together again. Sorry for the fan on the computer should stop in a second here. So finally, in September 2015, after 14 years, this ring was superconducting and powered to the full field. So it's amazing. We had to recreate all of that stuff back at Fermilab, but it was done. Okay, so in order for the experiment to work, we need muons. Okay, great. So we had to make muons, and so right. So we had to make protons. So we want to imitate what the cosmic rays do. So we made these high energy protons. They would be accelerated, and then we would take 1 trillion protons at a time, and they would strike a target, and they would make about 1 billion pions. So we saw those earlier in these cosmic ray interactions. The pions would decay to muons, and we would collect them using magnets. So kind of just like cosmic rays, except in a little more controlled way. And then we would separate out the non-muons, and send the muons into this. They would go around here, separate all the particles we don't want. Just like in the cosmic ray, you make a ton of other particles. So in this little delivery ring here, we would separate all the other particles so we could send a pure set of muons into the muon g-2 storage ring. Okay. So those muons would come in through the back here, and then the problem is we have to get them inside this ring. So there's the muons, we have to get them inside. And this is actually non-trivial, because if you send muons in, out here, there's a very weak magnetic field. In here, there's a very strong magnetic field. And if you send a charged particle through a magnetic field, it will bend. And so all of these muons we tried so hard to make are just going to fly away. So we need a special magnet called an inflector magnet. And its job is to prevent the deflection of the beam. And what it does is it just makes a magnetic field that cancels the magnetic field of the big magnet. So that there's zero field in here, the muons go straight in, and then they jump onto the ring. The next thing we have to do is, if we didn't do anything, then when the muons come through out of the inflector, they would go around in a perfect circle and then go and hit the back of the inflector. Okay, so we can't have that. Like when the muons are injected, they're at a slightly different orbit than when we want. So we want them to be on this blue orbit here so they don't hit the inflector. So partway through, about 90 degrees away, we have to reduce the magnetic field, and that makes the muons bend less. So instead of following the red track here, they follow the blue track, and that makes them go onto this blue orbit, and that way we store them. So the thing we use to do this are called kickers. We have 3 kicker magnets, and what they do is they reduce the B field, so the muons go from the red path, to the blue path. It sounds easy in principle, but here's what you have to do. You have to make a giant magnetic field, 220 Gauss, so that's 400 times the Earth's field, and you have to turn it on and off in less than a millionth of a second. Okay? So technically, that's incredibly challenging. Once we have the muons in the ring, then we have to keep them stored vertically. So just like that electron experiment, we need to apply some electric fields, so positive charges on the top and bottom, and that stopped the muons from going up and down, from leaving the ring. Okay, so how do we turn this all into this measurement of omega A? Okay, or the spin precession. Okay, so here's what would happen. Let's say we put the muons in. P is for the momentum and S is for the spin of the particle. If the G factor were identically equal to 2, so if Dirac was right, what would happen is that the spin and the momentum vectors would just follow each other as the muon goes around the ring. But the fact that the G factor is greater than 2 means that the spin vector is going to go a little bit faster. And so they don't remain locked together. And so this difference between the spin and the momentum vectors we call omega A, and it's proportional to the thing we want. Like this is what we want to measure, A mu. This is the magnetic moment anomaly. So you can see what we have to do is we have to measure omega A, that's the amount by which the spin vector goes faster than the cyclotron, and we have to measure the magnetic field. And with both of those, we can get A mu. So we measure 2 frequencies, the spin precession of the muons in the ring, and then we measure the magnetic field. And then we're done. We divide those 2 and we get A mu. That's the experiment. So this is what a muon sees. This is the inside of the storage ring. And these things here that you see on the left and right, these are the quadrupoles. Those are the things that keep the muons focused. Okay, so so we have to measure this omega A, the spin precession of the muons. So to do that, what we have to do is detect positrons from when the muons decay. So we have all the way around this ring 24 stations of so-called calorimeters. Their whole job is to detect when the muons decay, they produce particles called positrons. And we want to detect those. Okay, so how does this work? Okay, so here's the muons, they go around the ring, and then at some point they will decay, because remember, the muons don't last forever, and they produce positrons, and these positrons will spiral in and hit the calorimeters. Okay. Now, our job, remember, is we want to detect the muon spin direction, and nature's very kind to us here. When the muons decay, they produce a positron and some neutrinos. And the interesting idea is that the highest energy positrons are emitted in the muon spin direction. So they're telling us which way the muon spin was pointing. So this is what these calorimeters see. So this is the energy on this axis here of the positrons. And you could see that when the spin vector in red is parallel to the momentum vector, we get lots of high energy positrons. And when it's reversed, like over here, we get very few. Okay. So the number of high energy positrons tells us which way the muons are pointing. So it tells us, so that thing varies cosinusoidally, and in that cosine, its frequency is omega A. This is exactly what we have to measure, this guy right here. And it's just the cosine, it's just the frequency that the spin is going around. Okay, so what should the signal look like? Well, we have to take the exponential decay of the muons times the muon spin precession, this cosine term. So you take an exponential and you multiply it by a cosine, and this is what it looks like. This is what we call the wiggle plot. Okay. So you can see the exponential decay, and on top of the exponential decay are these wiggles caused by the muon spin going around. And we detect the positrons above a threshold. And so our whole job is to look at this thing, and we try to fit it and determine this frequency omega A. And if we can get that and we measure the B field, we can get A mu. So we took a lot of data and we spent 3 years analyzing that little plot back there. So there are lots of little corrections and things that we can't just fit it to this simple form. There are a whole bunch of corrections due to other phenomena, the fact that the beam is moving around and all sorts of some very subtle effects. So it took 3 years to analyze that data to extract this value for omega A. We also took 3 years to measure the magnetic field. And then there are lots and lots of cross-checks. So we have independent analyses. People do a blind analysis. We don't talk to our neighbors. We just do it independently and we see if we agree. It's years and years of work. And then finally, February 27th, we were ready to say, okay, what's the final answer? Okay. So I say we unblinded the result. Well, what does that mean? Well, you remember we had to measure 2 frequencies, right? The precession frequency of the muons, and then we also measured the magnetic field by putting protons in there and measuring how fast they precess. So we measured 2 frequencies. So we had a clock. One of the clock signals goes to the field measurement, magnetic field measurement. One of them goes to this omega A measurement. And the interesting thing was that this clock for the omega A measurement was blinded. So the actual frequency of this clock was not known to anybody in the collaboration, meaning that when I show you this wiggle plot here, we didn't actually know the time down here. It's like we took away all the time information. And so you don't know the precession frequency of this wiggle. It's hidden from us. And so however, it was known to 2 people outside the collaboration, and they would go in and check every week to make sure that this clock was doing what it was supposed to, but it had to be hidden from everybody else because we don't want to know the answer. We don't want to be biased in any way. So finally on February 27th, we asked, we opened up these envelopes that had the blinding factor that told us how fast our clock was actually running. Okay, and once we knew that, once we know omega A and we know the B field, we can get A mu, this thing that lets us test the standard model. Okay, so this was, you could just imagine, right? You've been working for, let's see, 2012, yeah, like 9 years on something, okay? And then finally, you're ready to look at the answer. And the experiment is so complicated. You can look at all of these different things we had to measure and put systematic uncertainties on. There's so many things in some ways that can go wrong that when we were ready to unblind, everybody was just super, super nervous, right? Here was the Brookhaven result. Here's the standard model result. And we didn't know, what are we going to get? Okay, so some of the options were, well, we could get the Brookhaven result and maybe have a discrepancy with the standard model. So that would be one option. Maybe we would confirm the standard model. That's another option. Or we could be somewhere in between. And then this is the one I was really, really worried about, was we would get something really weird, like way over here. Maybe we did something wrong. And this was the one I was so worried about because we've invested 9 years working on this, and to think that we had made some kind of mistake was just terrible. So that was, everybody's just waiting, and then finally we unveiled what we got, and this is what we found. This is the Brookhaven result, and when we unblinded, this is the result we got. So it's more like the first option from what I showed you on the previous slide. Okay. So here's the old result. This is what we found. And this is what the standard model prediction is. So what we did was we averaged these two results together. And this we call the best experimental, like what experiments are telling us is the value of the muon magnetic moment anomaly. So if we can combine the experimental results, this is what we get. And so this is what the combination of the experiments tells us. And you can see it's different than the standard model prediction by 4.2 standard deviations. Okay, so yeah. So fortunately, we didn't find something weird. We found something that agrees with the old experiment. Okay, but this is pretty interesting. I mean, this is now a lot of tension between the prediction and the measurement. So we found something consistent with Brookhaven. The combined result differs from the standard model prediction by 4.2 standard deviations. Now, we've only looked at some of the data. So this is the sort of data that we have. So this is in terms of multiples of the Brookhaven data set. So what I showed you comes from run 1. That's basically the same number of positrons detected as Brookhaven. But since then, we took run 2 and run 3. And though, after run 3, we had about 7 times the Brookhaven data set. Right now, we're in the middle of run 4. We probably have about 12 times the Brookhaven data set right now, sitting ready to be analyzed. And by the time we're done, we should have about 20 times. And so we should be able to do 4 times better than Brookhaven. So we're right around here right now. We're more than halfway done. So we're taking more data, so we should get an improved result. What would the improved result do? The improved result will let us shrink the size of these error bars. So these will get smaller and smaller. And so the difference between the standard model could get more significant. And the other idea is that whatever theory of nature should work will have to be consistent with this answer. So as we make it smaller and smaller error bars, it makes it harder and harder to make a theory that works. Okay, only one theory, or it's going to be hard to make the theories work if we do a better and better job on the experiment. So the other thing that's happening is that the theorists are also taking in new data, improving the calculations, and so they will make new predictions for the standard model. As new information comes in, and they figure out new ways to do things, the standard model result, its uncertainty bar should also decrease. And it could be that the center value here moves around a little bit, depending on what the theorists find. So the theory initiative is continuing to work, and they will update their theory estimate. Just as hard as the experimentalists are working, the theorists are working just as hard. And okay, thank you.
Oh, thank you, David. This is fascinating. I mean, it's very incredible. I have a lot of questions, but maybe I would like people to ask questions. Go ahead. If someone has a question, you can just unmute yourself and ask.
I have maybe an easy one. So the general appreciated amount in physics is 5 as the standard deviation. Can you talk a little bit about that? If it's under, is it? Yeah, can you talk a little bit about the significance of that?
That's a very good question. Yeah. So so right now we're 4.2 standard deviations away, and so probably the next thing we will release will use a result which combines run 2 and run 3, which will also be averaged with run 1. So that's about 7 times the data set. So the uncertainty will be about half of the experimental uncertainty should be about half of this. And that would start to become, we should be sensitive, I believe, at close to the 5 standard deviation level. Now the 5 standard deviation, there's nothing magical about it. It's just a sort of a standard that people have assigned. There's no magic in it. It's just that once you're 5 standard deviations away, it's really, really hard to ignore that something is going on. So I would say, it's interesting now, but if we shrink the error bars and it becomes, close to 5 standard deviation, then we really, really have to worry about what's going on. But that's an excellent question.
Thank you.
Akram, you raise your hand.
Yeah, thank you. Thank you again for taking the time to go over all of this with us. It was a great presentation. I
Pleasure.
do have a few questions. I'll leave it to maybe one or two. You can answer whichever one you want.
Sure.
So I read a few articles preparing for this, and I found one in Forbes magazine. Maybe you came across it, and it was about like the uncertainties about the project itself due to the R ratio. Maybe you can speak to that. And then the second question, which is I'm actually more interested in finding out from you, is if you do find that there are these unknown particles, what's the first thing that you're going to do as far as an experiment moving forward?
Okay, so the R ratio is is sort of what I talked about that we measure. The R ratio is this. I'll just go back here. Oh yeah, this is the R ratio here, omega A over omega P. That's what we call internally our R ratio, because we measure this, and when we multiply by some other constants of nature, and that determines A mu. So I'm not exactly sure what you're referring to.
Well, they said that because of the nature of the strong force, it's not that you can't measure it directly. It's like sort of an indirect measurement, and that it might contribute to some of the deviations.
Oh, okay, yeah. So okay, let me see if I have some slides. Yeah. So this goes to the theoretical prediction, and let me just see if I have some backup slides on that. Give me a second. I'm sorry. Yeah, okay, yeah, you're talking about the experimental input, the hadronic vacuum polarization, and okay, I did not, okay, I don't have that in this, I don't know why it's not in my plots here. Okay, let me just talk about that then. Yeah, so one of the contributions of the standard model prediction is the measurement of, oh, I know where I can get this. Hang on. Okay. So what you're talking about is this part here. This is the so-called hadronic vacuum polarization. And this is something that you cannot, well, until recently, you could not calculate this. And what we would have to do is measure the process of photons, virtual photons going into hadrons, and you would detect those. So you would scatter electron positrons off each other. They would make a virtual photon and produce hadrons, and you'd measure the cross section for this process. And that cross section, that's the R you're talking about. I'm sorry, I didn't understand at the beginning. And so that's a very, very hard thing to do. Those experiments are fantastically challenging, and you have to take those measurements and then convert it into the value of this hadronic vacuum polarization. Now, there's another technique for doing that using just computer calculations called something called lattice QCD. And there seems to be a difference between what the lattice calculations say and what the measurements say. So the data-driven approach versus the lattice computation. It's too early to say if that's going to persist. But there, for the moment, there's some tension between what the measurements tell us is the value for this term versus what the computations, like the computer-driven approaches, use. So that will be resolved over the next year or two, I imagine, because there are going to be multiple groups. Another group will come out with a lattice calculation of this term, and we'll see where that lands. Okay, so for your second question, like what happens from here? So as experimentalists, there's nothing for us to do except do a better measurement. We can't control anything. All we do is we'll measure. Now, of course, the theorists are very creative, and they will try to figure out, if this discrepancy persists, what could it be due to? So they are constantly coming up with models that could explain what we see. One of the difficulties is that, when we look elsewhere for differences in the standard model, remember I told you how successful the standard model is. And it's really crazy because no new particles have been discovered, no new forces discovered at the LHC or anywhere. Like, it's the standard model, it's very, you know, you should bet on the standard model is my idea, because it has won every single time. It hasn't failed yet. Maybe this is the first time it's going to fail. We will see. But you know, yeah, we'll see what happens. But the standard model has been incredibly robust. So for us, you know, we're going to keep measuring. The theorists will come in and try and make predictions that are consistent with our measurement, but also are consistent with all of these experiments that have excluded new physics, like all of the work at the Large Hadron Collider, which is, you know, absolutely amazing, has said that there's lots of physics that just cannot happen. Like this SUSY model here has basically been wiped out by the LHC. They just have not found these particles. So it's actually really hard right now to accommodate what seems to be new physics from G-2 with the fact that there's not new physics discovered elsewhere. It's really quite a challenge.
Thank you for that.
More questions?
Can you tell me what the lifetime of this muon is inside the ring apparatus?
Good question. Yeah. So since our muons are relativistic, their lifetime is boosted in the lab frame, and so they last about 64.4 microseconds in our storage ring, and so they actually travel many kilometers around in the storage ring.
Right, and without the ring, what's the lifetime of the muon?
Oh, so if you had a muon at rest, it would be 2.2 microseconds. So they live a factor of 29.3 longer because of because we make them at high energy, and so they're relativistic, and so they last longer in a sense due to special properties of special relativity.
More questions? Go ahead. So it's actually amazing how you can measure, I mean, both, for example, magnetic field with such a high accuracy.
Yeah, that's, I didn't talk much about that. That's the part of the experiment I work on. And so it is very challenging.
And also, if I can add a little bit, so the magnetic field should be uniform all along the ring, yeah?
Yes, so that, yeah, you bring up some very good points here. So that's the part of the experiment I worked on. So we had to, we spent a year taking this, you remember this reassembly video, there's these little pole pieces, and we had to adjust their position to better than 0.5 thousandths of an inch. And then we spent a year putting 8,000 little tiny pieces of iron to fill in little gaps in the magnetic field. So there were 10 or 15 of us just working for a year to make that field uniform, just for exactly the things you're talking about. Because if the magnetic field is not uniform, then every little muon sees a slightly different frequency as it goes around the ring. And so to make us insensitive to the muon distribution as much as possible, we make the magnetic field as homogeneous as possible. Yes, I didn't talk about some of those aspects, but they were, yeah, very challenging.
But this is very interesting because when you do experiment at such level of accuracy, it's beyond state of art. It's kind of,
yeah, you have to, so it's kind of unique, you know, you're exactly right. You know, it's the kind of experiment where, yeah, we care more than any other experiment about that sort of magnetic field, you know, except for the electron G-2, I don't think, well, they would care as much. And so, yeah, so we have to employ tools and take the time to do this just better than anyone else would ever care. So that's why there are 200 people in the collaboration. Everybody has a little job. I mean, you can just see all of the stuff we had to build, and it's really a big team to carry this all out. And everybody has their little job to make sure that their part works perfectly. It's really fun. It's very interesting, all of the effects that we saw. Like one of them for the magnetic field measurement, for instance, you know, if you try to measure the magnetic field in the storage volume, whatever you put in there perturbs the magnetic field. Like if you put a piece of metal in there, it's magnetized, and the magnetization will perturb the magnetic field. And so we have to consider all of those effects.
How much power is to maintain the fields, and how
Oh,
at which temperature that it is maintained in there?
good question. Yeah. So the ring, it's superconducting, but it still uses a power supply. It's not so-called persistent mode. And so there are 4 sets of windings. Each winding has 24 turns, and each turn has 5,200 amps.
Oh.
So it's a lot of
Energy.
tons of current, and the whole ring is at 5 Kelvin or so to keep it superconducting. Yeah, so it's a lot of current.
Ahmet?
Yes, Mr. David, I would like to ask, is this experiment dangerous in any kind of shape or form? Like, does the ring become really hot or too cold?
No. So the way it's a very good question. Like, how is it that you can keep something at superconducting temperatures, like 5 degrees above absolute zero, and yet the rest of the thing is at room temperature? I mean, you can see people walking around here, and you can touch it. It's just room temperature. So you design it so that the parts that are very cold, you keep them insulated from everything else. So you can use vacuum. Vacuum is a good insulator. And then where you do have to touch the coils, you make it in things that don't conduct much heat. But that is what, one of the biggest problems is heat load. Like, everything wants to make those rings warm up. And so you have to work really hard to keep them thermally isolated from the rest of the environment. And so you use vacuum and special materials and very little contact points in order to keep those two systems apart from each other. But so you're hitting on some of the very challenging technical things that have to be done.
Alejandra?
Yes, again, thanks for your presentation. Really amazing and really impressive work. I have 2 questions. Basically, my real interesting question is about the clock. When you mentioned the system, well, before that, you said you spent like 3 years on spin analysis of the muons and as well as magnetic field analysis, right?
Right.
But then you went to the part where you said basically where you guys didn't have the information with the clock. And that's sort of interesting because because basically the whole experiment was determining the frequency, if I'm not mistaken, right? Not the whole experiment, but like one of
Right.
the critical parts, right?
You're wondering about this blind. Yeah. So that's a good question. So we could do, okay, it's we picked this blinding value to be fairly small. Like it was really only different by less. It was picked deliberately to be within 25 parts per million of the true value. So we would not be affected by the fact, like none of the analyses would be affected by not having the true clock value. So it was chosen specifically so it couldn't cause any problems, the fact that we're sort of running with the wrong clock. It was just the clock that was used for when we record the hits in the calorimeters. And in a sense, it doesn't matter like how fast that clock runs. We're recording the hits and it's just later we say, oh, this is the time interval between the hits. And so that's the only thing that changed. So there were no physics implications of this clock being blinded, as long as the clock was working. And so that's what these guys here would check weekly to make sure that the clock was stable, even if it's not at the frequency we think it is, like at some unknown frequency. So it's totally fine to run that way. It's like if you make your watch run fast, and you can measure how quickly something happens, and then later someone tells you, oh, your watch was too fast, you can go back and correct your answer. It's not a it's not a problem for the physics. Yeah, there's no error associated with this.
Right. And real quick, because I think it's like everyone has been saying, the precision, the accuracy on your measurements is like something that's just not possible and to see every day. And basically, who's funding this project?
Oh, good question. Yeah. So in the United States, most of the funding will come from the Department of Energy and some from the National Science Foundation. And then our international partners have a lot of, I don't know many of their funding sources, but it's a variety of funding sources. It's a big job and took probably the whole thing was of order 40 to $45 million. Maybe
Wow.
50, I'm not sure. It depends on how you count because some of the money is just, to make a new building at Fermilab and to make a new beam line. And some of that stuff will be reused for other experiments. So exactly how you count the cost is hard to say.
Right.
It's of order $40 million, I would say.
Wow. Thank you. Thank you very much.
To sort of piggyback on that, I'm sorry. How do you justify the cost then to these parties that are, because that's what we were discussing yesterday. And I mean,
Yeah.
not to say that it's not needed or this work shouldn't be done,
Right.
but it's like,
we do have to justify this, right? This is funded by taxpayers. And so, we try very hard to do this. We don't waste any money. We transported the rings rather than making new ones and this kind of thing. Okay, and so you could ask, okay, what does the public get out of this ultimately? And like from my own perspective, the thing that makes me interested in this is, we learn more about nature. And part of that is just sort of inspirational. Like I think it improves people's lives just knowing that we know about nature. Like just knowing that you could go and ask someone, how does a star work? That there's, someone will know the answer to that. Or, how does a cell work? All of that sort of stuff. It's just great for people to know that this kind of thing is known. On a practical point, I would say that high energy physics has already justified itself because some of the things that came out of high energy physics include the World Wide Web, for instance. That was developed so that people at different laboratories, so at CERN and at SLAC, for instance, could send information across to each other. So, the World Wide Web is supposedly resulted in, trillions of dollars of economic activity. So I would say high energy physics has already paid its bill. But there are other things like the detectors. So, the detectors we use here detect positrons. Part of the developments of high energy physics was to make detectors for X-rays and all sorts of things like that. And those are all now incorporated in, CAT scan machines, PET scan machines. All of these things use high energy physics detectors. And the better we can make them, the more efficient and more accurate, the less radiation people would need to undergo. Another thing is just the accelerator. So now a new cancer treatment, it's not new, but it's been in development for quite a while, is using proton beams. You accelerate a proton beam and you can change the energy of the proton beam so it'll enter a human body and stop at a particular length where a cancer cell is. And so all of these things come out of high energy physics. And actually, let me go one more thing. The techniques we're using for the magnetic field measurement, that's called NMR. And of course, NMR is used in MRI machines. That's how you do human imaging. So a lot of the things people have developed have made their way outside of the context of high energy physics and just made their way into the world and have been very, very important. In addition to high, computing, handling large data sets, one of the outcomes of these sorts of experiments is you produce a lot of very highly trained people who are skilled in analyzing large data sets. And they can go on and work in bioinformatics, or they can go and work on Wall Street, they can do, whatever, but they're skilled in analyzing large data sets. So that, you develop human capital, we develop, physical infrastructure, and we improve our understanding of the world so that, so it's hard to say, exactly, this 40 million is contributing to all of that, but it's part of a bigger project that I think, it helps all of humanity, I think, ultimately.
that was a perfect answer. I think they should put you on the sales marketing team, get more funding, 40 billion, cut the check.
Yeah, I like the answer too. David, many students here, they're engineering major type of work. What kind of scientists work on this project and what kind of possibilities for students?
Okay, that's an excellent question. So yes, I did not highlight the role of the engineers, but there's another video, it's the one I cut off, that will show, okay, I'm not going to show you the big Moo video, but, you know, making this, right? You have to make a whole new building. You need civil engineers to design this, and you need cryogenic engineers to make the superconducting system. We needed engineers to design this, this rig that holds the ring. We needed engineers to make all of this infrastructure here. Like, the number of engineers involved in this is incredible. And the guys we had, the main guy, Del Elsbach, you know, is absolutely fantastic. None of this would happen without engineers. The electronics that we need to detect the signals from the calorimeters, ultimately it's designed by an electrical engineer. Like, we absolutely need these super, super smart engineers to do this stuff with us. So one thing, you know, students, you know, if you're interested in this kind of thing, I would highly encourage you to look at, and if you like, you know, this sort of context for the, you know, where your sort of work environment, you know, the national laboratories like Brookhaven National Lab on Long Island, and Fermilab and all of these places, they have a need for skilled engineers. Like, we really need, you know, really creative, smart, energetic people to work on some of the problems, because usually you're trying to do something new, and something that's usually very hard and something that's out of the ordinary. And so if you like that sort of challenge, if you really want to challenge, if you like to work on instrumentation or magnets or whatever, RF systems, national labs do some very, very interesting things. And I would highly encourage you to reach out. And they will have summer internships. They'll have a lot of programs to try and bring in skilled, excited new people to come and work on this stuff. So there are lots of opportunities. And so definitely look at the Department of Energy National Laboratory websites for positions and internships and that kind of thing. The other thing you could do is look at the website of the American Physical Society. I believe they have links to careers. And most of those careers might be for physicists, but they would at least show you places that are hiring physicists, which will often also be hiring engineers, or actually even sometimes prefer engineers. But there's, if you look at this, you can clearly see there's a lot of engineering involved here. Someone has to make all this stuff.
And David has, but maybe a couple more last questions.
Sure.
No one else, I have one.
Go ahead.
So let's say, just to make an idea, let's say it ends up getting closer to the standard model and we say, okay, we're awesome and it's close to what we predicted it would be. What types of implications are we seeing on, or are there any, on dark energy or dark matter or other things that we really don't know much about at all? Are there any?
Right. So that's a very good question. So yeah. So suppose we go, at the end of this, we find a value that's close to the standard model. Okay. So let's say the standard model prediction moves over a little bit, and maybe our experimental results kind of drift over a little bit. Then, some of the value we provide would be in shrinking these error bars. And so if you remember, like if you look at these numbers here, if you make a new theory of nature, it has to be consistent with these numbers. Okay. And so if in the end we get a number that's consistent with the standard model, what that would mean is that, if you make a new theory that incorporates some sort of dark matter, for instance, it would have to be consistent with the measurement. Okay, so it constrains what's allowed in your theory. So it's hard to say now, what the implications will be, but it does say that if you come up with a solution to the dark matter problem and it makes a new particle, we know that every single particle makes a contribution to G-2, everything. Some of the contributions are tiny, but it will make a finite contribution. And so if we shrink the error bars, that's starting to tell you, okay, you better not make your contribution too big because it has to match with the experiment. So it could be, so if we find something that agrees with the standard model, it's going to be hard. You know, we won't be able to prove or disprove, well, we won't be able to prove that a particular dark matter model is correct, but that dark matter model should be consistent with the experimental answer. Okay? So we can't say that that model is correct, but we can certainly say if it's wrong. And that's all we could do, yeah.
Thank you.
Suppose your values disagree with the standard model.
Mm-hmm.
What is that?
Yeah, so that's the tough one. And you know, if we find, let's say, you know, 5 years from now, 3 years from now, that we have a 5 or 6 standard deviation, sigma deviation with the standard model, then we really have to say that, okay, there's something new here. And the thing I didn't emphasize quite was that the size of this discrepancy is pretty big. It's as big as the contribution of these W and Z bosons, these weak interaction bosons, which are an important part of the standard model. And that's why this is so hard, because this is really big in some sense. Like it's hard to have this effect and yet not see new physics in other ways. But if it persists, if we really see it, then it's providing a little clue about what it could be. One thing people talk about is, and again, there are tons of models. There have been at least 80 papers since the experiment came out with possible explanations. One of them might be something called leptoquarks, where you know, the muon makes a leptoquark and a top quark and then interacts with the magnetic field, and then they get recombined. And that could perturb the magnetic moment anomaly. And the thing is, it's very hard to make these models. You know, you can make something that's consistent with G-2 and avoids the limits of the LHC, but it's only in little tiny bits of parameter space. And maybe that's the answer. Maybe nature works exactly that way, that, you know, nature lives in this little bit of parameter space. And maybe that's the answer. You know, we will find out. But it's hard. It just seems right now, it's very, very hard to accommodate what we see in our experiment and all of the constraints coming from the Large Hadron Collider and dark matter constraints. On the other hand, you know, you only need one model to be right, and that would solve everything. So it's hard to say. It's very interesting. We just have to keep doing our work, and we'll see.
Last question. Well, if not, okay, go ahead.
Right?
Mhm.
Imagine 4 o'clock Rachel, right? Imagine that Rachel.
I'm sorry, I couldn't hear that.
Yeah, me too.
Can I?
Yeah, go ahead, Alejandro.
Yes. Hi. So if you were to make a prediction from the standard models that the theorists come up with, what they gonna change if you were to make them predictions?
Oh, what will they change?
Yeah.
Well, what will happen is that the one thing that we will be able to tell, like just the size of this deviation and the size and its sign, you know, whether it's above or below the standard model, will tell the theorists about the size of the effect and some of the possible interactions. And so typically the size of the difference tells us something about the masses of the particles involved and their coupling to the standard model particles. So by itself, the Muon G-2 experiment can't say definitively, you know, what are the new particles, what are the new couplings, but it can say, you know, what, you know, if you make a new model, then you can test it versus the G-2 experiment. Like you can say, you know, if you know the masses of the particles in your model, and you know the couplings of the particles in your model, you can calculate its influence on Muon G-2 and see if it's compatible with the experimental result. So what people will do is, you know, if this deviation persists, it will tell them about, you know, the size of the couplings, like how strong this interaction point is here and what the mass of this particle might be here. But it will have to be, this result will have to be combined with other experiments to help hone in on, what is the exact model that can describe everything. So we will need lots of other experiments to point the way to the new physics. But you're asking, like, the hardest questions right now. Nobody knows the answers to those.
Yeah, if there are no more questions, maybe we can unmute yourself and just say thank you to David for such a nice presentation. It was extremely interesting.
Thank you. Thank
Yes,
you.
of course.
I really
Thank you.
appreciate it.
Thank you.
Thank you.
Thank you so much.
And congratulations on the accomplishment.
Thank you. And thank you so much for your questions and your interest.